Autonomous agents are colliding with software infrastructure built for a different era. We have reasoning models attempting to interface with rigid, deterministic endpoints. Historically, software boundaries were strictly delineated. We built user interfaces for human perception and APIs for programmatic execution by other machines. Exposing these standard REST or GraphQL endpoints directly to a large language model creates immediate operational friction. The model is forced to rely on manually written system prompts. It frequently guesses parameter structures and executes commands without semantic safety boundaries to prevent destructive actions. This diagram maps a third architectural layer. Between the UI for humans and the API for servers, a space opens for a cognitive interface. An AI agent doesn't think in endpoints. It operates on intents, searching for tools that match its goal. This requires a specific standard. Apcore is a schema-enforced module framework designed to build tools that are inherently perceivable by AI. It moves beyond simple endpoint mapping by structurally embedding identity, operational strategy, governance, and error recovery natively into the module's definition. The philosophy of the standard is linear. When an interface is structurally perceivable by the model, it becomes understandable. Once understood, the AI knows how to use it. Enforcing strict schemas at the module level converts standard backend functions into natively perceivable infrastructure. This bypasses the fragmentation of bespoke AI server integrations. To achieve this perceivability, standard backend functions require a specialized envelope of structured metadata. Looking at the three-layer metadata design, it begins with the core layer. The apcore standard enforces an input schema, an output schema, and a functional description. Enforcing this layer ensures the model understands the module, satisfying the agent's discovery phase. The second tier is the annotation layer. This is where developers inject behavioral context. Tagging a module with attributes like read-only or destructive establishes immediate tactical boundaries, so the AI knows the operational weight. Setting the requires approval annotation to true establishes a governance checkpoint. The agent will pause execution and request human confirmation for sensitive operations. The final tier is the extension layer, functioning as a free-form dictionary for custom inputs. This acts as tactical wisdom, mapping common mistakes or specific scenarios to plug directly into the AI's strategic planning lifecycle. If an execution error occurs, the specification utilizes an AI guidance field within the error payload. This gives the agent a precise path to autonomously correct its inputs and heal the process. This tripartite metadata stack provides the context necessary to elevate a basic API endpoint into a self-describing cognitive tool. Defining this architecture on paper is distinct from implementing it in a live codebase. Developers typically face friction maintaining separate JSON schemas to map their backend functions for LLM consumption. Here is the apcore integration path. By adding a single decorator over an existing function, progressive integration is achieved with zero modifications to core logic. The framework automatically infers the input and output schemas directly from the existing type annotations. Beyond individual module definitions, these tools must be organized into a cohesive, system-wide identity. Managing tool orchestration across an enterprise-scale system with hundreds of potential agent actions quickly becomes a routing bottleneck. Apcore resolves this with a zero configuration mapping principle called directory as ID. We see a project's standard file directory tree here. Standardizing the file structure dictates the module's identity. The path dictates the exact namespace used by the framework and the AI to invoke the tool. Removing boilerplate and automating schema generation ensures the application's source code acts as the strict source of truth for all AI tooling. System architecture must reconcile a core tension. Non-deterministic AI reasoning models must interact with strictly deterministic backend execution layers. This is the apcore execution pipeline. We can trace the flow of a request from the moment the AI decides to invoke a tool. The first checkpoint is the access control list. If an API layer attempts to bypass the orchestrator to hit the execution layer, the request is immediately denied. This configuration enforces a hard governance boundary against LLM hallucinations, forbidding unauthorized cross-layer module calls, regardless of what the agent attempts. Clearing the ACL, the request enters a nested middleware loop for preprocessing, executes the core module logic, and exits through post-processing validation. Traveling alongside the request through this entire pipeline is a persistent data environment, the context object. Looking at the context schematic, it carries the structural data required for deep observability, notably the trace ID, caller ID, and call chain array. The universal trace ID allows developers to map exact execution paths across complex, multi-agent interactions in distributed environments. As one module internally invokes another, the call chain array automatically accumulates this data in real time, preserving the full lineage of the action. This pipeline guarantees that even when deploying fully autonomous AI orchestrations, the operations remain sandboxed, measurable, and auditable. The current ecosystem is fracturing. Organizations are independently rolling out their own custom model context protocol servers, creating isolated, incompatible standards. APEcore's strict schema enforcement solves this by decoupling the structural definition of the tool from the transport layer used to invoke it. This creates a build once, invoke anywhere architecture. The core module sits centrally, streaming to distinct nodes. A standard MCP server generates instantly for tools like Claude, requiring zero interface rewrites. Simultaneously, agent-to-agent exports enable standard-compliant communication across distributed AI swarms. This specification provides absolute cross-language parity. The same behavior and routing logic is implemented identically across Python, as well as TypeScript and the Rust programming language. This SDK-first standard stands in direct contrast to the brittle server-first development cycle currently dominating the AI integration space. Building resilient systems for an agentic future means designing infrastructure that expects to be perceived by non-human intelligence. Scaling parameter counts in language models does not address the underlying lack of structured metadata. Effective autonomous engineering relies on the standardized cognitive interface layer provided by apcore.